Sí, no, si no, ya está. Precisa assinar.
Fica aqui, depois vai fazer.
So, hello, everybody. Thank you for being here. I will host this presentation. We'll make an introduction, a brief introduction in English, and then I will pass the word. So, thank you for joining us again. This week is a week full of events, and today is one more interesting event to attend. So I will, without further delays, I will present our guest today. Our guest is Manuel Arnas. He's going to make a presentation about Industry 4.0, HPC, high performance computing, and big data. Manuel Arnas is a brief bio. Is a CEO of Apentra Solutions, a company. Startup company, professor at the University of Coruña in Spain, has a PhD in computer science from University of Coruña on advanced compiler techniques for automatic parallelization of scientific codes, and recently has co-founded Apentra Solutions to commercialize products and services that take advantage of parallel, a new technology used for analyzing scientific HPC codes. So I will pass the word and thank you for Manuel's availability to join us today here. I will pass the word to you. Thank you very much. Yes.
Boa tarde. ¿Puedes oírme? Creo que sí. Bueno, es un placer enorme para mí estar aquí, recibir esta invitación para presentar lo que estamos haciendo en Coruña no mercado de High Performance Computing y cómo relacionamos con Industria 4.0 o Big Data, creo que es local. Encantado de estar aquí. Bueno, paso entonces a ver un poco lo que es mi presentación. Ya paso ahora a inglés para poder tener mayor difusión a través del streaming que nos estáis contando fuera de aquí. So, when I was invited here, I mainly was asked to try to relate what is our main work in the University of Coruña, my research, and the work we are doing now in Apentra Solutions, the startup we have created, participated by the university, and related to these trending topics: big data, industry 4.0, deep learning, artificial intelligence, all of these main topics, keywords that sound in the media, but how do we relate this to parallel programming and high performance? So I have tried to make a brief introduction and come across a good article, I think, where it gives you a trend of how we have gone from parallel programming to now this terms big data, AI, and deep learning. So this will be mainly the focus of the first part of my talk. And I will try to also give a brief introduction to the current trends in the hardware and the software that are pushed in the market because of the demands of the learning, artificial intelligence, these new killer applications based on high performance. Then I will try to make you an introduction of what we are doing in Apentra. Basically, how do we are trying to help to build better scientific software, because it's very complex to write good scientific software because it changes very fast. The specification is not really clear because the researchers are really trying to figure out in their minds how to solve a given problem. They have to model this problem and code the problem in the simulation code that runs in a computer. So this is a discipline where traditional software engineering techniques are hard to apply because of this lack of a good specification in what we have to build as computer or software engineers. That will be the focus of the second part of my talk. And finally, I will try to explain you our experience in Apentra, trying to build business in this very competitive high-performance computing worldwide, trying to sell and build a product that provides high value to national labs in the US, companies in Europe, Spain, US, and across the world. Okay, so these are some of the things we are doing or we've been doing since we incorporated the company now 5 years ago. Okay, so to try to understand what's going on behind in the market right now, I came across this blog post by the CEO of Rescale, that is a company operating in the high-performance computing market in trying to sell cloud services. And he talks about, the CEO talks about cloud 1.0, cloud 2.0, and cloud 3.0. So I think explains in a good manner what is going on right now. So cloud 2.0 is typically native software as a service that we are really used to use right now. When we go to when we hire a new service, we don't want typically now to buy the software that has to be installed or deployed, because this needs systems that are in our headquarters or in our organization. We need the staff to maintain and update these hardware systems and these software systems. So it is much easier to deploy the software as a service, so that the client doesn't have to take care of or take into account all of these issues. And this is pushed to the company that is providing us with this service. Okay, so there are companies that were born recently and are native SaaS companies. Examples are Salesforce, that it has a client relationship management system, or NetSuite or Workday. These are only a few examples, but these are companies that are performing very well in the market, and they have these high growth curves that typically investors or typically have high visibility or awareness in media. But there are traditional companies that have been here for more than 20, 30 years that are struggling to try to adapt all the corporation, all the organization to this new SaaS or cloud-based, native cloud-based market. So examples are Adobe. In this post, they highlight how Adobe 2 years ago managed to change everything inside, so that now their products and their services are sold in a more SaaS manner, more native SaaS manner, and this has provided them a great increase in the price of their shares in the stock market. So this is a clear value of how the value provided by this company has changed dramatically by adopting the cloud SaaS approximation. Okay, and now we have also Microsoft, IBM, HP, all the big traditional IT companies are trying to find a way to move to the SaaS or to the cloud market. Cloud 2.0 is big data. The change here is that as we have using SaaS application, we have everything ready to be used at any moment. Now we have our smartphones with many applications where we generate hundreds of files, hundreds of videos of media that is stored somewhere in the cloud. But somehow this is producing a huge amount of data that has to be processed, because in the end, many of the services we are demanding right now, and we are willing to pay for them, is other services that process this data and give us some conclusions, some insights into this data, so that we can take decisions for our corporations, for our institutions, or even for us personally to take decisions of a person for our family. So this is the basic idea behind big data: scaling and connecting the full stack data layer. All the software, all the technologies that were developed to process this massive amount of data have somehow are now deployed as a service, again, that is typically called infrastructure as a service. So all the data and storage services that were deployed because they were demand for the SaaS native applications are now available to us in the cloud. Okay. So this is cloud. Big data is cloud 2.0. So now we are moving towards cloud 3.0. It's big compute. Instead of having data accessible everywhere with applications or with software to process data and get insights into them, now what we need is to have compute available everywhere at any time and guaranteeing performance to our applications. Some time ago, when there was a decision that someone had to take in the organization, that is, do I buy my own cluster and install it in my system, or do I hire an external service that gives me that? And typically, the access to the systems, external systems, have an impact on the performance of me working or the simulations or the things that we were running or trying to solve with my code. So now the big challenge here is how do we make computation available to everybody, anywhere, in a guaranteed advertise as big compute. So big compute is the motivation for HPC, that is typically a niche market. Very few big players moving many dollars every year, but are solving the needs of a relatively small amount of people. Okay, how do we move for these technologies to the big markets? Big markets are persons like me, or like all of you, that are using applications with the smartphones or with the laptops or with desktop applications. Okay, for personal use or for corporate use. So in this regard, deep learning is supposed to be the first killer application to apply big compute and HPC technologies to the big markets. That's the reason why all the big vendors, Google, Microsoft, NVIDIA, Intel, IBM, all of them are pushing, are fighting to be the first that is able to provide these big compute services. And they are focusing mainly in artificial intelligence and deep learning. So all the hardware that is created, here we have different types of hardware that we can find in the HPC market, and at some point they will move into the mainstream market. We have these traditional CPUs. On the opposite side, we have the tensor processor unit recently developed by Google, and in the middle we have the NVIDIA GPU, the FPGAs of Microsoft. There is a variety of devices that will be available in these infrastructures in the cloud, available for me to purchase the configuration of the setup of a cluster in the cloud that provides me access to all the compute capabilities to run in my organization for a personal use. Okay, so deep learning is the first killer application that is motivating the development of these big compute technologies by all the main vendors. And here we can see as NVIDIA pricing of the shares in the stock market has increased dramatically since they changed from being a GPU company to be a deep learning company, because they are now using these technologies. They can sell the GPUs not just to big national labs in Europe or in the US or in Japan. They are selling it to the big industry, Amazon, to Microsoft Azure, all the big vendors that are giving these services to the public, that is us, me as a person, and you as an organization. Okay, so I think this is interesting knowing that services, we are now in the big compute area, we are entering this big compute. So this is the main motivation. So what happened behind the scenes from where I can provide some insight, that is the HPC or the high performance computing field. So I will try to summarize what are the hardware trends and what are the software trends, so that we can have more or less a clear view of the type of simulations that are being run in the most powerful systems or supercomputers available in public national labs or in private corporations. So let's begin with the hardware market. HPC is always about building the most powerful supercomputers that are more powerful than the supercomputer that was built last year. Okay, so the next milestone of the HPC market is building the first exascale supercomputers. These are supposed to be 1,000 times more powerful than the most powerful supercomputer today, and to consume much less energy than the most powerful supercomputing available today. Okay, so this is really a huge effort that is all the big geographical areas, US, Europe, and Japan and China, are fighting to be the first country or the first region to build the first exascale supercomputer. Okay? So this is a slide of the exascale computing project in the US. This on the left, we have the current systems for instance, in two national labs, in the Orange National Lab and in the Flores Livermore National Lab, with the setup of the hardware setup. And these are on the right, they are the next systems that they plan to build. Some of them are being deployed during this year or next year. But in the end, what they want to build is the first exascale supercomputer within 5 years from now. Okay, more or less by 2020 or 2022, 2024. It's very difficult to know exactly when the system will be built. Just taking a look at some of the articles in the media of HPC, we can see that there is a hot topic that is how every company positions with providing value with a given device that differentiates from the rest. So Google is pushing the tensor processor unit, NVIDIA is pushing the GPU, Microsoft is pushing the FPGA, NEC, other company, Japan, is pushing new vector architectures that are very similar to those that existed in the 80s, but updated to the current needs. So there are a lot of systems, different types of hardware devices that are available for us to purchase and to set up a supercomputer of our cluster. And this is a ranking of the top 100 list, where we can see that the most powerful supercomputers today are essentially massively parallel systems, combining some type of multi-threaded CPU with some type of devices, FPGA, GPUs, intensive files, some type of accelerator that provides a massive amount of computational power. So this is what's happening from the point of view of the hardware. The question is, I am a computer scientist, I am a computer engineer, how do we program these systems? What kind of tools do we have available to write a code that can run in the system and perform and take advantage of all the computational power that we have available in the hardware? So the motivation again, as for exascale compute project, is building the most powerful supercomputer, exascale supercomputer. What applications will be running on the supercomputer? Essentially are scientific applications that are running at the frontier of the knowledge in the area where they are being developed. So we have applications that are simulating these supercomputers in almost every single market segment. Okay. So, for instance, in aeronautics, in the 80s, we have Airbus to design a Boeing 747, I think. They had to build 40 flags just to try to decide which is the flag that is going to be built and deployed with the aircraft. So, using simulation and HPC, they build simulation software so that they can simulate almost everything, and instead of manufacturing 20, they can manufacture only 4. Imagine the reduction in cost in order to build the final flag wing that will be available in the model they want to release. Okay? So this is the only example of the impact that simulation in big supercomputers can have in industry and is having in industry. And of course, don't forget that simulation is the only option in those areas where we want to make research, but we cannot touch it with our hands. So for instance, from the point of view of the spatial domain, what about simulating the universe? Something that we cannot touch. So we need simulations to understand and have a better understanding of what's going on in our world. And also, from the time dimension, what happens on the molecular level or at the microscopic level, nanoscale, where we cannot really touch what's going on. But we need to understand that to create new nanomaterials, to create new materials for our clothes, for instance. Okay? So here, the HPC applications are the only alternative for us humans to have a better understanding of what's going on in our that is planned by the exascale compute project to program and develop HPC applications for the future exascale supercomputers. So imagine all the libraries, tools, frameworks, IDEs, middleware that has been currently developed in this project to achieve the goal of having a software stack so that we can develop software and take advantage of all the power of exascale supercomputers whenever they are ready. Okay? So imagine the complexity of what's going on in the development of the software. But to be practiced, if we are focusing on scientific simulation, that's our area of expertise, that's the kind of target market we are approaching with Apentra. Essentially, everything comes down to selecting some technologies that are the ones that are used by current exascale applications, but that's supposed to be, again, the technology that will be used in the future exascale applications. So, in the end, the model that is prevalent today is having distributed memory at the first level using MPI, the message passing interface, to connect and interchange information between different processors running in different nodes of a cluster or different nodes of a supercomputer. Okay? But imagine that some years ago, a node of a cluster was only a CPU, multi-threaded CPU. But now, this node of a cluster are 4 multi-threaded CPUs or many core CPUs like the IBM Power 9 system, accelerated with 4 voltage GPUs of NVIDIA. So we have a huge computational power within only one node of our cluster. So how do we exploit this within a single process that is running on one node? We need a second level of parallelism that is usually exploited using OpenMP. There are several technologies available, several options, but MPI plus OpenMP, this combination is supposed to be one of the leading technologies to program future, current of course, and future exascale. Okay? So these are the focus of our work in Apentra to try to help scientists to develop MPI plus OpenMP applications in a more productive manner, in a more easy manner, trying to achieve the performance that they need to run the simulations in the time they need for the products. Okay? So this is more or less the context where we are right now. What motivates the current market trends, what we have in the hardware, what we're going to have in the hardware, and what we have in the software stack, what is being created, so we can program this simulation or these applications to run in this current and future system. So the problem here is now that the code that is being simulated, that's being created, is being created mainly for research. So research, as I said before, many times the specification of the problem is not clear or changes very fast. So creating good production level software is very difficult because the specification changes, and this impacts in all the software design that software engineers have. So we have a compromise in scientific software of creating good software with a good quality, but in the time constraints of it. Okay? So we have really a problem of what is with the quality of scientific software because of the nature of the scientific software. So there is a big effort again in the US and worldwide to try to push good practices or best practices in software engineering and adapt them to the needs of the scientists that are creating these applications for the supercomputers and for the future exascale supercomputers. And this is the part of the second part of my talk, the topic of the second part. So here I'm trying to, I have reused some of the slides that I used in marketing and in business when I was at conference, so my apologies if this is too business oriented, but I have tried to take some of the materials that I have so I can explain what we are doing right now. So what we are doing right now is we are developing a technology that is called parallel. Okay? But we are a startup company. So as a startup company, our problem is that we don't know yet what product we're going to build, what product we're going to sell. So we need to build it as fast as possible to try to find a market needs that pays for us. Okay? So we have, after 3-4 years having feedback from the market, we have decided that Parallel Trainer is the first tool that we can sell in the market. And this tool is oriented to people that is not familiar with scientific software, not familiar with MPI, OpenMP, OpenECC, the different technologies that are used to create HPC applications, and help them self-train and help them learn how to use these technologies and apply it to the code they are implementing, the code with which they are making the results. Okay? So if we take a look at this pyramid, the lower part of the pyramid is the traditional way in which we, for instance, at the university, make courses. There's a teacher speaking, many people listening, taking some notes, and that's it. After that, we have moved, maybe we have small exercises trying to apply what we have seen in the theoretical lectures. So the next level is learning, self-learning of technologies of any topic is making this lecturing more interactive. So we usually make hands-on sessions where we create materials, we create labs where we put an example that is not very naive, but is quite complex and can be solved in the time that we have for the lab. And the students have to struggle in applying what they have learned to a real example that can be solved in that time. So this is what we call the workshops on the participating interaction. But we still have slides, lectures, and labs that are not connected. So we don't have interactivity in learning and having feedback from what the user is doing from the teacher. Okay? So what we're trying to do is we are trying to learn what the hackathons are doing. What the hackathons are doing, the hackathons are at the top of the pyramid. These are very expensive type of training because we have a very few amount of people in a room, maybe 6 teams, 2 people, 6 teams, 12 people for 1 week with mentors, with expertise in everything they can do, so that the mentors can help them in just 1 single week go from nothing to something that runs in parallel or even that uses a GPU. Okay? So this is very expensive. So what we're trying to do with our training is taking the benefits of the hackathons and pushing this down to the lower levels of this pyramid. So we can capture somehow the best practices in parallel programming, make them available in a tool so that the user can interact with the tool, playing with code, making modifications, compiling, executing, testing, everything that is needed. And without the direct interaction with the lecturer. So they can do it for self-learning in an autonomous manner. Okay, this is the main mission or the main goal that we are pushing. So this is the current UI of our tool. Looks like a software development IDE, but it's supporting the different stages of the HPC software development cycle. We will see it in a later slide. So what are these phases of the software development cycle? First, the first problem that you have is you're addressing the understanding of a code, probably not developed by you, developed by someone else. So you have to first understand the code, analyze the code, the file, the organization, the headers, how everything is built to compile and execute that can be run. So this is usually a very difficult and very stressing state of the work for anybody trying to port or to develop a parallel application starting from an existing sequential. Okay? So the second step is, okay, now I understand the organization of the code. Where should I focus? If I have 100 lines of code, I know where I have to focus. But what if I have 1 million lines of code? Where do I begin? I need to identify what are the parts of the code, the regions of the code, that are really good opportunities from the point of view of parallelization. So that if I can translate the sequential code into a parallel equivalent, I can have a big impact in the overall performance of my application. Okay? So this is the second step. Once we know this, we still don't have a version running in parallel. We have to implement the parallel algorithm. We have to design it and decide if we want to go to multi-threaded CPUs, to FPGAs, to GPUs, if I'm going to use MPI plus OpenMP, or I'm going to use any other library or any other technology available out there to program it. Okay? There is kind of a very complex design stage with decisions I have to make that will have a huge impact in the implementation that I finally have to do. Okay? So this is step 3, introducing parallelism, deciding where I want to go, what technologies I'm going to use, and in the end, coding these applications in parallel. Okay? So learning the technologies, learning how to use them, and learning how to apply them to my code. So these 3 steps are really very, very complex in practice. So finally, we have the 2 steps for testing. Don't forget that when you go to parallel, the first thing you have to do is test for correctness. You have those changes in your code, and many times we're focusing on how much I am reducing the execution time of my application. And many times I find it with my students in the University of Columbia, they reduce the time by a factor of 2x, but the numerical result is incorrect. They have forgotten about testing that the numerical result is correct. So that's the first thing you have to do once you have a parallel implementation. And when this is correct, then you have to worry about performance. Am I 2x faster, 10x faster, 100x faster? How much faster I am? Okay. So in the end, the final performance tuning stage is: am I faster enough? I am being requested to program an application 20x faster, and I'm in 10x. I still have a gap of 10x that I have to address. Okay, so this repeats all the steps, repeats in an iterative manner. Every time you decide to pick up a new region of code and try to parallelize. Okay. So to understand this, the first two stages, understanding, and now I'm going more into the parallel programming area of my talk today, and that is somehow at the core of big data, deep learning, and all these HPC technologies. So basically, the main problem is that when you are trying to address the parallelization of a code, you take the output of a compiler, you select GNU, you select intercompiler, pre-compiler, and you try to gain from the output of the compiler, try to figure out if that part of the code can be executed in parallel or not. Okay? So this is the kind of output you will get from these tools. For a very simple code of 6 lines of code, you are presented with a huge amount of information in the report, and some things that tell you this is sequential, this is parallel, and when it is sequential, it is parallel because there is something that is called a dependence, an anti-dependence, an output dependence, or two dependence, something that is very theoretical, and this is the theoretical background of compilers. So this is outputting the messages to the user, but this is really difficult to apply in practice in our code, and to use this information to really decide how to rewrite the sequential code in a parallel. Okay? So what is missing here is another tower in the split, that is the code tower. So this is what we did. So we hide the dependencies information from the user, and we talk to the user in terms of something that is more understandable for humans, that are called patterns. We look at the stars, and we see a pattern that is called as some stars that have a given shape, and we identify that as a shape, as a pattern. So patterns help us to understand almost everything for humans. Okay, so why not use the patterns to learn and program parallel programs? Okay, so this is what we are doing with parallel technologies. So this is the current UI. We have a parallel console where we have all these messages. Instead of talking about dependencies, we talk about parallel star reduction. This is a kind of pattern, fully parallel loop, temporary variables, some kind of thing that still need explanation, of course, but are easier to understand for us as humans. Okay? And that are more easily related and linked to the code we are writing when we are modifying. And this is a very simple example. Just 10 lines of code. What you can expect as output from this first stage. That is, if you have to parallelize this, you at least have to decide which is the output, which are temporary variables that have an impact in the output of the code where this routine was called. And you have to analyze the code to identify all this information. So why not having a tool that helps you in this step? Introducing parallelism is quite more complicated. Once we know the kind of pattern that we have, for instance, a parallel scalar reduction, a parallel star reduction, there's a family of patterns that we have identified. So now what we have in the UI are several dialogues where you can just, by clicking, choose some of the parameters of your design space. Do you want to go to CPU or GPU? Do you want to use OpenMP, OpenACC, or other technology? Do you want to use multi-threading or floating? And this design space is supported in the tool. And once you have decided this, we also support different parallel implementations of the same pattern. So you can generate different parallel implementations, try them, test them for correctness, test them for performance, and decide which is the best that you want to select to keep on working on it. Okay? Of course, they are not perfect solutions, but they are, if you have to travel all this path, are a first step so that you don't have to make everything. You can start for 50, 60, 70% of the work done, depending on the features of your scientific application. So here we have an example with multi-threading on a CPU with OpenMP. All this OpenMP stuff, it doesn't matter if you're familiar or not, are notations in the code, but I set it automatically, just in what's in the link. If you want to go to GPUs, just change the design space and offload your code to GPU using OpenMP signals. Different annotations, but now you can compile and execute on a GPU. or you can use OpenACC. You have different annotations, but again, you can compile and move and execute your code on GPU. Okay? This is the kind of added value we are bringing with these tools, based on the power of technology. And of course, also in the end, we have this part of the UI here, so that you can, from the UI, you can build your code and execute your code locally in your laptop or remotely in a cluster. The setup of the tool enables you to do this. Okay? So, this may seem to be magic, but of course, as a first product we are releasing, has many limitations, is doing many things that no other tool is doing, but we have many limitations. So now we will try to go into the strategy of Apentra, how we are trying to collect feedback from the market, from the users, from the universities, from the labs, how we take this feedback, and how this impacts on the technological roadmap or the development of hardware and the development of the UI. So we can change the features of the tool so that we can have it ready to sell as soon as possible. Okay? So in order to do this, we have been doing this for 3 to 4 years now, and we are still working on making refinements of the UI and the technology to fulfill the requests of the client. So let me go just into 4 or 5 of the things that we are doing. I don't know how much. It's okay? Sorry? Okay, great. So one of the things we are doing, we have been doing during the last year, is we created an early access program. Basically, what is this? When you create a startup, I did a research in the university. I made a technology transfer agreement with the university to create a company. I am the CEO and the CTO of the company, so I have to take decisions of it. So basically, what we need is to be very agile, very lean. We need to go out to the market, test the tool, have the feedback from the users, so they say, I don't like this, I don't see any value of this. This is very useful, but I need you to change this. This kind of feedback is difficult to collect because usually you have to sit with people to see how they're using the tool, so you can really collect the feedback that is useful for the development team. Okay? So in order to do this in an easy manner, apart from contacts and meetings with people in the labs, we created this early access program where for free you can register, you can download the software and try it in your Linux operating system. The software at this moment is released only for Linux operating system. So during 1 year, we have been able to collect feedback from almost 90 participants around the world, from labs, universities, and companies. And all this feedback had an impact, a very clear impact on the technology roadmap that we will see in the next slides. But the most important thing for us as a company, we need to tune the product so that it's ready to sell. So one of the things more complex for us is to really explain why what we are doing is valuable in the language that scientists can understand. So the hackathons and these passing courses, everything, all the activities we have done in person, has really offered us the opportunity to speak to people. So from these hackathons and from these activities, we were able to close the first 2 sales of our company after 5 years of creating and developing this tool. Okay? So this is the kind of measurement that is really good sense for us because it means that we are going in the right direction. We don't have many sales, we are not self-sustainable, but we're going in the right direction because someone is willing to pay for what we are doing. Okay? So we will keep on doing this kind of activities during the next year and the next 2 to 3 years. So the hackathons are a central point in this. We started doing it in last year. We are organizing the second hackathon next week. One team from the ICAR is going to be there. And basically what we are preparing is an agenda for help them to take a code and have a parallel version running, if possible, on GPU only in 5 days. That's our challenge to help them do that. But also, the challenge for them is also to help us in giving us feedback on how to use it, how useful it is. If it is useful, they will use it. If it's not useful, why it is not useful. Give me your feedback so I can improve it. Okay? So the hackathons enable us to have big technical discussions and big discussions with teams so that we can really know the needs that they have in the daily work when they go back to their universities or to the labs. And it's the opportunity to create a strategic relationship with institutions in Spain and around the world. Okay? So these are basically the things that we are looking for when we organize this hackathon. So we have now this second hackathon next week, and we are planning also the organization of our second hackathon, again in Tesla, in Supercomputing Center, probably in September this year. Okay? And this is the most successful team that we had in the first edition. It's a team from the University of Malaga. They came with an application running sequentially to simulate tsunamis. And basically what we were looking for is training people in a group of 8, 10 people, so that there are not only one people that is responsible for maintaining the code, but they have at least 2, 3 people that can modify and adapt the code so they can meet the constraints of the contract they have with the NOAA and the event testing. Okay? So this is mainly the application they presented. I wanted to focus only on, we had them to identify the pattern. Their code didn't work in the parallel version, the parallel trainer version we had 6 months ago. So we had them still to understand it from the point of view of the pattern. They came up with this pseudocode. With this pseudocode, they learned how to really use and implement these parallel patterns in parallel in CPU and TPU. They learned with very simple examples with the parallel trainer. And at the end of the hackathon, they moved this to their application and they found these results. Look at the results for the big problem sizes. 100,000 finite elements is a finite element application, running 7 times faster on a multi-threaded CPU, and running almost 6 times faster on a GPU. So even if the tool doesn't work for the application, we can still help with the methodology based on patterns and learning with the tool how to program and how to code a pattern so it can later translate it into their application. Okay? So we hope to find new successful stories in hackathon where we are conducting next week. And this is the hardware trainer roadmap. When we started 2 years ago, we have engaged with the big national labs in Spain with the Barcelona Supercomputing Centers, in the US with the Orange National Labs, with the NERSC Supercomputing Facility, the Lorenz Livermore National Lab, with the Jülich Supercomputing Center. And what we have learned is that for these people, that is really busy people, to dedicate time to us to understand and help us to know what features do we have to implement, we came to the conclusion that we have to write papers with them that have to be published in the main conferences so they can have real feedback from them. Okay? So this is the strategy we are doing with these people to try to refine and adapt the technological roadmap that we have for our development team so we can develop new features. Okay? So this is available in our website. You can see all the details of what we have been doing, but all the features we're supporting right now. 1 month ago, 2 months ago, we released the last version, and all the upcoming features that are at the bottom of the slide, the upcoming features we are working on, that are our response to requests for the clients of future clients. And again, we are aware we have many limitations in the kind of applications we can support. So at this moment, we are supporting C applications or C++ applications coded in a C style. That is a typical case in the HPC applications. But now we are also working to move up these columns in the programming language features that we are supporting. So we are beginning to work with Fortran, we are beginning to work with C++ so that eventually at the end of the year, we can release a version that can extract patterns and help to parallelize your code, not only for C, but also for Fortran and C++. This is our technological roadmap for the point of view of supporting the programming language features. And these are the results of, you may ask yourself a question, how many patterns do we have out there? Hundreds, tens, 2, 3? So one of the studies we conducted with these labs, analyzing many applications that they use, the color benchmarks in the Department of Energy in the US, we came up to the conclusion that mainly we know we have a battery of 15 patterns, but only 3 patterns are used in the parallel implementations developed by experts that publish in this code. So we have analyzed these parallel implementations. We have come to the conclusion that these 3 patterns, each of them can be implemented in 3 different manners in the real application. So this is what we call the best practices to try to port your code to parallel for sequential parallel. Okay? So these are the kind of features of knowledge we learn and we support the tool. So we are supporting at this moment these 3 patterns, and for each of them you have the possibility to generate 3 different parallel implementations of each of them to test them for correctness, test them for performance, to iterate in the next iteration of your software development life cycle tailored for HPC. Okay? And of course, other limitation that we have is that we are deploying the tool as a classical, traditional desktop application. We are not a SaaS native company, but we are in the very beginning of the company. So we are beginning to plan how to move the technology, removing or as an alternative to the desktop application that you can install in your Linux system, deploying all the technology, deploying all these best practices, all these options through a native SaaS application. Okay? So this is the kind of things we're beginning to specify right now to try to build it during next 2 years. Okay? So what we're doing here, essentially Parallel Trainer is supposed to be a tool that where you can self-learn parallel programming using these technologies. So these technologies are essentially parallel programming is about learning a language, C, C++ or Fortran, and translate it into a parallel one, C plus OpenMP, C plus OpenACC. So it translates language A to language B. So why not looking at native SaaS applications that are helping humans to learn languages? Why not looking at what they are doing in native applications to learn Portuguese, English, Japan, or Chinese? So there are some applications that are native SaaS applications to learn languages that are called Duolingo, Babel. There are several ones that probably many of you are using in with your smartphone. So this has very interesting features that we can apply also to learn parallel programming. We have a set of lectures, a set of courses, is lectures with theoretical contents, with labs that you can experience. So why not Parallel Trainer providing maybe with a framework of courses and lectures with the labs, where for each lab, in an integrated environment, the user, the people that is learning, can play with the lab, test it, go into sequential to parallel, test the performance, all the features that we have seen in the Parallel Trainer application. Why not doing this in a cloud native manner? Okay? So this is one part. The other one, interesting feature is progress metrics to measure the progress of the person. If I want to know how good I'm performing in learning Chinese, in learning English. So these are the metrics of progress that all these tools have, and we can want to apply also this idea to learn how far away you are from having a good expertise in using OpenMP with C. You are in a newbie level, intermediate level, or advanced level. So this kind of thing is the one that we are beginning to think about. Okay, and of course, going to cloud as a SaaS native. Okay, and just very briefly to end my talk. What we have seen here is we are using the Power technology as a black box. The Power takes decisions as what patterns you can find, gives you options to design your parallel application and to implement it. But this is good for learning, but HPC experts don't want black boxes. They want to know everything that is going on inside the technology. What are the facts about the code, the key features about the code that the technology used to take the decision. So that they can say, okay, I'm confident with this, or I want to override the decision because I know I'm the expert, I know what I'm doing, just will do it the way you have decided to do it. Okay? So we are beginning to create prototypes of a second tool that will be released to the market eventually next year. It will be called HPC Sonar. Essentially is all the information that is collected about the code for the Power technology, that is hidden in the Power technology, Power Trainer product, has to be shown, presented to the user, to the developer, so that they can see all the properties and all the features about the code that have been analyzed, and decide whether this is correct or not, provide additional hints that the technology could not collect for you. Okay? And that's it. I hope not that you found this presentation interesting. I have tried to cover many things very fast and trying to fulfill the request from the organizers to try to relate parallel programming to this BigData, HPC, Industry 4.0, deep learning, training topics that we can see in the video. So thank you very much, and please, questions.
Well, now we have the opportunity to make
some questions. Well, yes. So, anyone? Please.
Hi, congratulations for your talk. Thank you for coming. My question is not about only the use of the platform that you are creating. That sounds very interesting. But when you are dealing with some of the problems that require high processing are related to use machine learning and deep learning and so on. And most of them are using also external libraries. And so you have to mix the code that you create by your own with the code that you are using from others. And sometimes you don't have the skills or the knowledge to change the frameworks or the libraries that you have. How do you think we could mix these on the optimization of of solutions that use that kind of your own code and the external code that you are embedded in the solution and the optimization?
So the question is about general optimization of applications.
Yes.
That essentially are applications that are using external libraries. You are not a programmer of the external library. You're using it as a black box, just calling some functions of the API. Okay, for the short answer is I cannot give you a general answer because it depends very much on the features of your application, the way you call it. For instance, if you are using deep learning, for instance, and you're using the TensorFlow library developed by Google to program this deep learning, this tensor cores of the NVIDIA GPU, the question is, how do you use this in an application that is making calls to this library? If in the end what you have is when you analyze and understand your code and you come to the conclusion that that single call takes, I don't know, 80% of your code, of your running time, then there are a few things you can do apart from going to a more powerful hardware with more code, with more GPUs, because the libraries are usually supporting multi-GPUs and supporting complex hardware configurations. But for instance, if you come to the conclusion that calling to this library is again, 80% of the execution time, but not for 10 calls, but for 1 million calls, then what you have is that each call is just having a small execution time. So now you have a problem that you need to analyze the context in your code, how these calls are being called, and if somehow you can rewrite your algorithm and your own code to call it in a more efficient manner or with more bigger problem sizes that you can really take advantage of this library. And usually this library is now many of the efforts in the exascale compute project are about rewriting very popular libraries so that they are natively supporting multi-GPUs, multi-threading, syndication, vectorization, all the features that you can see in the hardware. If you make that single core library, if the hardware is available, it is supposed to exploit everything that you have. So that's that's a way to approach parallelism. But if your application calls these libraries now highly optimized in many different ways, in many different times, then you have to go have a bigger, analyze a bigger region of your code and try to optimize across different calls of the library, of the same code, or across different calls to different routines from different libraries. And that is usually very, very big because you cannot touch nothing outside. You have to take a look at the interface, what are the inputs, what are the outputs, and how you can redistribute your data, your computation to try to make them work together in a better, more efficient manner. Indeed, when you write hybrid code with MPI plus OpenMP, adding OpenMP stuff is easy. Adding sometimes MPI is much more complex, but it's easy. But it's the combination of two in large codes and how, when you have parallelized MPI and different regions with OpenMP, of this part, but how they interact with the others, one with another, is the complex part of addressing building hybrid applications. And usually when you first program hybrid applications, you cannot expect to increase the performance. But essentially, you usually begin with a big slowdown, and you have to tune many things to begin to go up and up and up. You will not go like this or something like this. Okay? I hope to have answered your question.
Any more questions? Further questions? Well, I can make one or two. You are talking right now about the MPI, the OpenMP interfaces or techniques to make parallelization. How is the state of the parallel software introduce both? It's just an OpenMP basic solution, or it's targeting an hybrid approach?
For Power Trainer, to help you go from sequential code to parallel, it can annotate the sequential code for you, providing the code with parallel semantics, as was basically with OpenMP. We can do this automatically. Once you give the clicks of the different design options in the design space, if the code fulfills the constraints of the features of the C programming language that we are supporting, we can help you with it. We generate automatically from C plus OpenMP code, C plus OpenACC code. What we do not generate is C plus MPI code. And for MPI,
it has to be done by hand.
Sorry?
It has to be done by hand, manually or by the programmer. So the developer.
What we are now working on is we can analyze sequential C code. We are working with the team during these weeks to prepare the hackathon to see if we can help in analyzing code that already contains it. So you have already have an MPI code. We are struggling to see how we can help you to find bridges of code that can take benefits of OpenMP. But again, this will have to be revisited because of the question of when you go to hybrid, you usually have something like this, and you have to see how all the different OpenMP regions couple with each other, how they interact with it. That's the first question.
Yes. The other is how generic and how commodity can be the use of a solution to an everyday programmer's problem, in the sense that your slides were showing basically scientific computation problems that typically use HPC. And in the beginning, you had a motivation that is how to expand the possible customers or users of this application to go beyond the niche players that are scientific communities and scientific. So, what is the point? What is the status that right now is having a solution that can be used by everybody to improve our standard application that we do? I was thinking like, well, now there is a trend, and we have it. We are also teaching that in our courses that is, for example, mobile programming. So now everybody wants to make a mobile application. Typically, what we have in mobile devices, we have more than a single core. So typically, we program a sequential code that might have networking, so communication with sockets or messages. Then it might also have a graphical user interface call. And this is a typical GUI application on the mobile environment, which is a very trendy thing, and our students are very fond of making projects on that particular market and type of devices. And how far away or how close are we from having a possible solution, probably from your company, that can pick up an application, a traditional standard sequential application like this, in order to improve it and to make use of the cores of the device, mobile device?
Okay. We are focusing on HPC traditional market. So we really don't know what other technologies or languages, programming languages that are using this tool available. So as long as you program in C with an API and you use OpenMP or the technology we are supporting, and the code in the end where we are is the tool provides you a different version of source code. So we are helping you to improve the performance of your software. So you have set up all the software stack to build applications for these mobile systems. And as long as they support these languages and these technologies, basically we are providing you with a new version of your source code. So there should be no problem or no interaction, no limitation in using the frameworks that we're using. I don't have any experience in what kind of languages they're using.
I was focusing this question on of the commodity software that the typical programmer nowadays does, not niche applications. So the question was like, so the mass market, if you have a solution for a mobile environment, you have here 90% of customers asking for your application. So that's an interesting. It's a subject that we could talk about later on.
Yes, of course. Very interested in talking about that. Basically, what I can tell you is, as we are addressing the HPC market, we are developing things in the short, in the medium, and in the long term. So in the long term, what we can see is that a trend in the developers that is building using Python to build highly productive and very fast big applications. But Python is not efficient for parallel execution. It's very inefficient. So the current solution right now, even in the HPC market, is we have Python for high productivity for developers. Once this is done, this is developed, they do the profiling, they search the hottest spots, they understand the code and decide where they want to focus. And when you want to exploit all the power of supercomputers or of even a simple CPU for a Python application, Python is providing you with values for C and Fortran. So in the end, it's you that have to write your Python function with a C or Fortran equivalent, and the Python environment has bindings to compile everything, that everything goes, and you can build the application in a very similar. But if you want to go for peak performance, right now with Python, you have to go through C, which are the traditional. So for us, in the short, medium term, supporting for C now, supporting Fortran, C++ with a C-like syntax, not very advanced things are used software engineers, but those features that they use for scientific programming, and of course, at some point addressing Python, or why not even R, this language that is so popular for the statistical field. And there are movements now. We are basing everything we do on the LLVM infrastructure, and we are beginning to see papers in conferences about LLVM, about Python, about R, of how to produce R LLVM code from Python, LLVM code from R. So we are now working with the centers to produce LLVM code from Fortran, and we have LLVM code from C and C++. And all the core technologies on LLVM. So once we have these bridges, the different languages, of course, there are many technical issues that have to be taken into account, but this opens the door for our technology to be applied and used in Python, in R, C, and the main languages, multiple languages used in this. That's more or less what we're looking for.
Yeah, it's a
Long term.
I don't know if there is any further question. May I ask something?
I would like to ask one thing and comment. If I can start with a comment. Representing here our master's degree, we are completely interested in exploring this kind of tool. So we talk this later. But the question is, you mentioned that one of the hardest parts in your process is to identify the part of code that could be parallelized. And you're working on creating mechanisms to help the industry to identify those parts. So can you help me select those parts of code to be parallelized? And if so, if I normally program follow a particular kind of patterns, will believe will be possible in the future that you can do that by yourself. And you don't focus my code. I focus on patterns, and you try to find my patterns and try to parallelize my code. Do you believe it is possible? So should I teach my programming C to our students? Using it or parallelized?
That's a good essential question. What should we teach our students? Sequential programming, because it's mainly all the engineering stuff in the industry or in the academia knows sequential programming. But of course, there are many alternatives intrinsically parallel languages. So there is a trend that is, why not helping our or teaching our students not to think in sequential manner to later address the parallelization, but to think in parallel, with parallel elements that can be later implemented with a sequential language and parallel, or with a massively parallel intrusion. Okay? But I think that's a discussion that pretty much depends on many things that are not related to technical issues, but more political issues or business or academic issues. So that's an option of, that's something you have to decide. Teach sequential and teach how to go from sequential to parallel, or teach it directly. I think that both approaches are interesting, because in the end, when the students right now go out to the market, even if they think in parallel, maybe they are the only person thinking in parallel in a group of 10 people that think sequential. How can you fight against the inertia of the team you're working with? So I think that teaching both things are very, very important. Other question is about the patterns. I see two questions from what you're answering. The first is, should I teach the patterns? There are many different kinds of patterns. If you go to the specialized literature, you can find tens of different definitions of what a pattern is, and different taxonomies or hierarchies of types of patterns according to that philosophy. What is different in the patterns we are detecting, we are using, is that these patterns do not depend on the scientific domain. For instance, a pattern may be matrix-matrix multiplication. A pattern may be the FFT. We teach matrix-matrix multiplication, FFT, how to make optimization of them. And in the end, we can see big applications calling a library that executes a mapping multiplication or executes an FFT, and how they interact with each other. So this is a type of pattern. But the problem with this type of pattern is that it's dependent on the scientific field, okay? On the physics field or mathematics, not physics. The patterns we use do not depend on the scientific field, depend only on the code. So the advantage of this is that when we say we have a pattern that is called parallel sparse reduction, 15 years of experience, we know that if you come to our hackathon with a finite element applications at the Danja group of the University of Malaga, we knew from the very beginning, even not taking a look at the code, that we will be parallelizing a parallel sparse reduction. Because we have been making research with mathematicians and physicians working with the finite element method. So the finite element method is applied in many different scientific fields. So in these scientific fields, in the end, the way they program, they code the finite element method is using a parallel pattern that is called the parallel sparse reduction. We have also found the same pattern in finite volumes, in particle methods. So in the end, you have many different types of methods using physics and math. That in the end, when you go to the code, that's the reason why this is so important. Go back to this slide. This one. When you focus on the patterns in the applications tower, you have hundreds, different types of applications, and many different hierarchies of patterns you can find. But when you go down to the code, what you find is common patterns across many different scientific fields. So this is why what we're doing is potentially so powerful. So we detect the patterns in the code. So we know that if you come to the hackathon with a finite element applications, we are 95% sure that we will be addressing a parallel space reduction in the application, in the parallelization state. The other question is, so that's the answer related to patterns. The other answer is, the other question is, a parallel star reduction. In how many different ways programs can code a parallel star reduction? I have done an exercise when I lectured parallel programming in the University of Columbia. I took 20 students and I asked them to write a simple matrix vector multiplication. Freedom of choice to use within C or the features they want. Eventually, they came up with 20 different implementations of the same matrix method. So essentially, it is the same pattern. But the complexity of the tools that we are doing to detect and help you to understand your code and discover the pattern is that we can code the same pattern in an infinite manner. So for instance, you can code it without functions, without structs, without classes, without templates. You can mix all of these features in many different ways. But in the end, it is the same matrix method. This is why what we are doing is so challenging. It takes years to get ready to be mature enough to release one of these projects. Because the technology is discovering all the different implementations we have found so far in our application to find different parallel implementations of the same parallel pattern. So this is what we want to do with the parallel core technology behind HPC Sonar and parallel training. So when the tool and the maturity of the technology cannot do this automatically, we have this perspective. This is the reason why we need to organize this hackathon to really help you with that. And we know that giving you only the tool for simple code can help you, but for mini apps or almost real code, it's very difficult that we can help you at this moment in a senior field because of this. I don't know if I have answered all your questions. Okay.
Well, if there is no further questions, I think we can thank you very much for our guests and see you tomorrow.